All right. Well, I'm glad you are all back in spite of how bad Monday was. I'm using a different laptop now that gets better throughput, and I haven't had any problems since I switched to this one. So we should be good. And looking at the material I had planned to cover for today, it looks like I've got enough time that I can cover stuff that was from Monday as well, to give us kind of a better view of what we talked about on Monday. And then we'll go ahead and cover today's law of cosines. So let me go share the screen I've got here. And I talked about this. I think it's still probably coming up. I talked about the types of triangles and how we name them, angle, angle, side, and so on. There we go. So you can see these are the 5 triangles we've got, and I mentioned that the top 3, the types of configurations that we might use law of sines on. So if we have angle, angle, side, that's a good one for law of sines. Angle, side, angle is also good. And then we've got side, side angle. Now conceivably,
are you going to post this on Blackboard so we can maybe print, or I guess it's in the book?
This is in the book. It's page 557 of the book.
Yeah.
So you've already got a copy of this. And I was just about to point out that some people might call this angle side side, but the acronym might throw some people off. So we call that one side side angle. And then the other 2 we've got are side angle side and side side side. These 2, the bottom 2, are best for law of cosines, which we will get to a little bit later today. The top 3 are good for law of sines. And notice the text they've got here by this third option, the side side angle, is that there may be no solution, 1 solution, or 2 solutions. The case with 2 solutions, they call the ambiguous case. Now I'm going to jump to a different page in the text where they talk about those multiple solutions. This is on page 561, where they're going to talk about these options. So if angle B is acute, meaning an angle B is the one they gave us, we may have no solution such that the angle comes up, side B is too short, it never reaches this horizontal. So there is no answer where that's going to work. It might have 1 solution where B is just long enough to barely reach that horizontal side. So we get 1 solution. It may have 2 solutions where B is a certain length, but it could hit at 2 different spaces. That's ambiguous. Either one is a valid solution, and so we may have to list both solutions. We may have exactly 1 solution where B is just long enough, it's the same size as C in this case, or it may be longer than side C, such that we only get 1 case. Now, if angle B is obtuse, it again could be no solution, or it could have 1 solution where it comes down and just touches. And I know this says no solution here, but clearly there's a solution. They show us 1 in the picture, so I think that's a typo. And so we need to consider all of those cases. And so what I'm doing that seems to work in most of my other Collaborate classes that I've been doing is I'm using Photoshop to write and share some of these pictures so that I can share it without having to hold up a whiteboard and worry about glare and so on. So let me go ahead and switch over to Photoshop here so that I share that with you. And I've got a graphics tablet, so I should be able to write on here as if it's a pen, and the text seems to be working pretty well for most of my classes. So let's take a look at some of these cases that we've talked about. In this particular problem, and I'm just pulling one out of the book, in triangle QRS, we're given that side Q is 15. We're given that side R is 28. And we're given that angle Q. See, the technology for me today, though, has been a little odd. And angle Q is 43.6 degrees. So what I do is I just draw a triangle. It won't be right, but it lets me visualize what's going on. So it's triangle QRS. They tell me side Q is 15, side R is 28, angle Q is 43.6 degrees. And now I could use law of sines to find angle R. I'm told I need to solve the triangle, so I need to find the missing side and the missing two angles. So I could use law of sines here, and it would be sine of an angle. So sine of the 43.6 degrees divided by the side opposite it, which is 15. And that equals the sine of an angle. I don't know angle R, so I'll just write that over the side opposite it. And so we have a nice proportion. We can cross multiply 15 sine R equals 28 sine 43.6. Divide both sides by 15. So sine of R would equal all of that. Let me plug that into my calculator. 28 sine of 43.6. Divide that by 15. Gives me 1.287. Which doesn't exist. Sine is never greater than 1. Sine is only between 1 and negative 1, right? Our unit circle has nothing greater than that. If I took the arc sine of this, I would get an error. So it turns out that there is no triangle with an angle of 43.6 degrees whose opposite side is 15, along with another angle whose opposite side is 28. This is a no solution, which we saw was one of the cases we would run into. Now I stopped there, but I ought to probably go ahead and take the arc sine of that 1.287, and as I expected, I got an error, out of domain error, because sine will never be greater than 1. Sometimes we'll do all of that work and end up with no solution. That happens. And somebody said they lost audio. Can anybody hear me?
I can hear
I
you.
lost it a minute ago, but I had to log out and re-enter the session to be able to get it back.
Yeah, I hear you.
Okay, good.
Okay.
Yeah, I
Oh.
hear too.
Good, good. So I think we're doing okay. All right, so that's one of the cases where we have no solution whatsoever. Now let's go ahead and look at a different case. One nice thing about Photoshop is I can clear things out really easily, but the other information is still there. We can go back to it if we need to. So let's look in triangle XYZ, we're given that side X is 23.5. We're given that side Y is 9.8. And we're given that angle X 39.7 degrees. Okay. So once again, I'm going to go ahead and draw a triangle. And you know what? My triangles always look like this. I don't know why. I think that in my mind must be the definition of a triangle. It doesn't matter. I know the sides are going to work out. The math works. So this is 23.5. This is 9.8, so clearly not drawn to scale. Angle X is 39.7 degrees. And now we'll go play with some math. So once again, I need an angle in the side opposite it for this to work. So sine of the 39.7 degrees over 3.5 equals the sine of y over 9.8. So we've got a proportion. I can just cross multiply. 23.5 sine y equals 9.8 sine 39.7 degrees. Divide both sides by 23.5. Sine of y would equal whatever that is, go into my calculator, 9.8 times the sine of 39.7 divided by 23.5 is 0.2664.
Should we have our calculators set to radians or degrees on this?
Notice that we're given 39.7 degrees, and when that's the case, you want it in degrees.
Okay, I just want to confirm.
Yeah. If you see the degree symbol, then make sure you're in degrees.
The
So
cross
this tells-
multiply method,
Yes?
that's different than what's in the book. So could you explain that a little bit more?
Yeah. Anytime I have a proportion, which is two ratios or two fractions set equal to each other, a nice way to solve that is to cross multiply. So you take the denominator of one side and multiply it by the numerator of the other. And that's on one side of the equal sign. Then go ahead and write the equal sign, and then the denominator of the other one multiplied by the numerator of the first one. And so anytime we have two fractions set equal to each other, we can work it out this way. The denominator of one side times the numerator of the other on one side of the equal sign equals the numerator of the first one times the denominator of the second. And then it's just algebra at that point. Okay. So now my angle y would be the arc sine of the point 2664, which comes out 15.45 degrees. So that's our angle y. Now, I don't know why it keeps jumping that way. I need to fix that somehow. I will. So the question is now, do I need to use the supplement of this? What is the supplement of 15.45 degrees? Let's see, 180 minus 15.45 is 164.55. 164.5. Now, if angle Y were 164.55 and I added that to 39.7, I would be over 180. And recall that the sum of the three angles has to be 180. And so I can't have two of them add up to greater than 180, and that tells me that this option is off the table. I don't have to consider the supplement. I know that Y equals 15.45. Let me go ahead and change colors since that has to be the case, because the supplement would not work inside this triangle. So I only have one solution with this particular triangle, which is nice. So angle Z is going to equal 180 minus the 39.7 minus the 15.45, just because the three angles need to add to 180, and that is 124.85. So that's angle Z. And they probably tell me to round to the 10th. I don't remember. But I would follow the rounding that they ask for in my math lab. So let me come up here and type this in. Okay. So now the only side we're missing is side Z. And so I could use law of sines again. Now I'm going to go back to the givens. I'd rather go back to that as often as I can and not try to use my calculations. So I'll go ahead and do, again, sine of 39.7. Let me zoom out a little. This might give me a little more space. So sine of 39.7 degrees over 23.5 equals sine of 124.85 over C. Again, I can cross multiply. So I get Z sine 39.7 degrees equals 23.5 sine of 124.85. And now I can divide by sine of 39.7. The sine of 39.7 will cancel over here, and Z would be that calculation, 23.5 times the sine of 124.85 divided by the sine of 39.7. And that gives me 30.19, so I'll say 30.2. So this would be 30.2. Wow, that zero is terrible. All right. So that had one solution. It didn't have the no solution we had with the first one, and it doesn't have two solutions. We checked that because the supplement of our angle Y would not work with the 39.7, which is the test I always do to determine whether or not I might get two solutions. is I look at the supplement of the angle I got and see if it would work. If it gave me, if that plus the angle I had left enough room to have another angle and still sum to 180, then I consider this two options. If the supplement won't work, then I only consider the one. Do you have any questions on this one? Okay. I'm going to go ahead and jump over to law of cosines right now. We can come back to law of sines later if we need to. I just noticed we've got half an hour left, and I wanted to be sure we had enough time to cover this. All right, so back to Photoshop. I'm not going to derive the law. The derivation is in the book. It's on page 569, and the derivation comes from the distance formula, where distance was the square root of the sum of the squares of the other two sides, or the difference in y squared plus the difference in x squared and so on. But the law itself has three iterations. You've got c squared equals a squared plus b squared minus 2ab cosine angle c. That's one iteration. The other two are extremely similar. We might have b squared here, a squared plus c squared minus 2ac cosine angle b, or we could have a squared equals b squared plus c squared minus 2bc cosine a. So let's talk about the differences between these. You'll see they're not great, the differences. In each case, we've got three letters, A, B, and C. If we look at c squared, and to be honest, I only memorized this first one. Since we can label these sides and angles whatever we want, I just go with C on this side and I label my triangle appropriately. But we've got c squared equals the sum of the squares of the other two sides minus 2 times the product of those two sides times the cosine of the angle opposite the side that's on the left-hand side of the equal sign. And it's that way for each one. Notice when we had b squared on the left side, we're taking the cosine of b, and a and c, the other two variables, show up in these locations. When we have a on the left-hand side, we're taking the cosine of angle a, the other two variables being b and c, those show up in these locations. So as I say, I really only memorize that first equation. So let's see how to use these. If you'll recall, one of the triangles that has us do that is the side angle side. So let me go ahead and draw one. Say we've got this triangle. We'll do A, B, C. And we're given that side A is 32. Side B is 71. Side C is, or angle C is 32.8 degrees. And we're asked to solve the triangle. So I'll use law of cosines. I've got a side angle side. So c squared, this is side C here. C squared equals a squared plus b squared. So 32 squared plus 71 squared minus 2 times 32 times 71 times the cosine of angle C, which is 32.8 degrees. That I can plug into my calculator. And when I do, let's see what I get. 32 squared plus 71 squared minus 2 times 32 times 71 times the cosine of 32.8 degrees. That gives me 2245.47, which is huge, but I need C, which is the square root of that, which is 47.4. And that fits better with the sides we were given. I believe that that is a viable solution. And change colors to write that in here. So this is 47.4. Now I need these two angles, A and B. That's all I'm missing. And to be honest, law of sines would work really well for that. So I could do 32 over sine A equals 47.4 over sine of 32.8. Cross multiply. And I already know there's one solution, so I don't need to consider the two solution option. 47.4 sine A equals 32 sine 32.8. Divide by 47.4. I need to figure out why that's jumping and get it to stop, because that's bugging me. 32 sine of 32.8 divided by 47.4 is 0.3657. So A would be the arc sine of that, which is 21.5. And I expect the smallest angle to be opposite the shortest side. So that makes sense. This third side would just be 180 minus those two, minus 32.8 and minus 21.5, and I get 125.7 for angle B. So that's how we would solve that. Let me scroll down.
Yeah. Is that all that the law of sines consists of then?
Law of cosines?
Yeah, that's what I meant. Law of cosines.
Yes,
Okay.
that is the law of cosines, and that's all there is to it. Which is why I figured we would have enough time to talk about some of that stuff from law of
And then
sine.
for the side, how would you go about finding the angles then?
Yeah, let's do one of those. Before we do, are there any questions on this particular problem? Okay, I'm not hearing any. So let's find a side, side, side problem and work that out. All right, so I'm given, I like to use the triangle RST. Let me zoom in just a little bit here. Triangle RST, I am given that R is 3.5, S is 4.7, and T is 2.8. Okay, so let's draw a triangle. Side R is 3.5. Side S is 4.7. Side T is 2.8. All right, so let's get an angle. Our formula says C squared equals A squared plus B squared minus 2AB cosine C. We don't have A, B, and C. We have RST, but I can pick whichever one I want and plug those in as long as I get them in the right spot. So let's go with the 4.7 over here. That'll be squared. 3.5 squared plus 2.8 squared minus 2. Scroll over, make sure I've got some space. Times 3.5 times 2.8 cosine. Now, C is this angle opposite this over here, opposite the left-hand side, opposite the 4.7 is, I think I just figured out why it's messing up on me, is S. So I'm looking for S. We will have, let me get cosine S by itself. Let's see, we would have, let's go ahead and just square everything first. 4.7 squared is 22.09. 3.5 squared is 12.25. 2.8 squared, 7.84. 2 times 3.5 times 2.8, 19.6 cosine S. All right, so I need to subtract these two, and then I need to divide by negative 19.6 on both sides. So 22.09 minus 12.25 minus 7.84 is 2. Divide that by a negative 19.6 gives me negative 0.102 is cosine S. So I'll take the arc cosine of that, and I get 95.85. or 95.9.
Okay, so we subtract, we came out with 2, then we divided by the negative 19.6, and that gave us the negative 0.102,
102.
and then we
Yep.
took the arc cosine to get the 95. Okay, I just wanted to confirm. Yeah, I'm just trying to write it all down, so it's...
Yeah. Arc cosine is valid in the first and second quadrants. And so we're not going to have that ambiguous case where things are not, where we have to look at the supplement. Arc cosine will always give us the answer we wanted, which is nice. Now we could use law of cosines again. That's an option.
Can you repeat that? Does that mean that in the law of cosines there's never an option of 2, or just in this particular case?
In law of cosines, we will not have two answers, two possible answers.
All right, thank you.
It's much nicer that way. Law of sines has that one case when we've got a side angle where we might have two, but law of cosines will only give us the one answer, and it will be the right one. So we've got...
Sorry, one more clarifying question. Could you repeat what law of sines where the two options can happen?
Yes, it happens in a side angle. And I got that from page 561 in the book.
Thank you.
You're welcome. Now, as I said, we could do law of cosines again here to solve for t, or we can go to law of sines. Either one will work for us. Once we've got the one angle and we've got all these sides, law of sines will only give us the one option. But we could do law of cosines. Maybe we should, just to get some more practice. So I could say that if I'm plugging in the other letters, t squared equals r squared plus s squared minus 2rs cosine t. The most important bit is that I get the letters the same on the outside of law of cosines, and the other two letters fit into those spots. So we've got 2.8 squared equals 3.5 squared plus 4.7 squared minus 2 times 3.5 times 4.7 cosine t. So doing the same sort of arithmetic we did up here, I'll get what's on the left side of the equal sign equal to cosine t. It's like plus 2.8 squared minus 3.5 squared minus 4.7 squared. And I'm going to divide that by negative 2 times 3.5 times 4.7. And that gives me 0.8055. So t would be arc cosine of that, which is 36.3 degrees. Up here. So T would be 36.3 degrees. Once I have those two, I can subtract those two from 180 to get R. 180 minus 95.9 minus 36.3 is 47.8. And I expect the longest side to be opposite the largest angle, the medium side to be opposite the medium angle, and the smallest side to be opposite the smallest angle. So I think we've done a pretty good job here. Those answers fit for me. I'm comfortable with that. And so those would be the answers I would enter into my math lab. Have you any questions on those? All right. Law of cosines I enjoy a bit more than law of sines. And again, I just memorized that first iteration because as you can see here, we can apply it to any side as long as what's on the left side of the equal sign is the side opposite the angle we're taking the cosine of. We're going to be okay. And we're given some application problems with this that gives you a chance to practice it. In those, you'll want to make sure you draw a picture so you can visualize what's going on with the triangle. They may ask you which law would work best with a given problem. And so you'll want to refer back to, what was that first page I showed you, 557, I think. Yeah, 557 shares with us which law works best.
Is there any chance that you could refresh at least my memory on when we're solving for this, if we're supposed to solve the angles in degrees and minutes?
Oh, that's a good question.
Because
With
that's
this
been the
particular,
homework in my math lab. And since it's been a while, I've been kind of struggling with that.
with the degrees and minutes. Okay. Yeah, let's take a look at that. There's enough room here, I can just add to this. So it's more the converting with degrees and minutes.
I'm sorry, could you repeat that one more?
Was it kind of the converting degrees and minutes over to something we can use?
Yeah, like, so in my math lab course for homework, it just had us doing, like, for the law of sines, I haven't gotten over to the law of cosines, but to the law of sines, it just had us, solve the triangle, but they wanted it down to the nearest minute. And so I just, since it's been a couple months since we've done that, I've just been kind of pretty tripped up over I was only able to do the first problem.
Okay. So I'm trying to find something in the book so that I can work straight from there. If we're given, say, 18 degrees, 28 minutes as one of the angles, what I would want to do is convert that over to decimal degrees so I can just type around in my calculator. And then when I'm done, convert that back. So let's see how we would convert this. So minutes, we know there are 60 minutes in a degree. And so I need to convert this. So what I'm going to do is I'm going to take that 18 degrees and I'm going to add to that 28 divided by 60 degrees. Do a little dimensional analysis with that. We've got 28 minutes. I know there are 60 minutes in 1 degree. And so setting it up this way, the minutes cancel, and I multiply across the top, 28 times 1 divided by the numbers on the bottom. That's how I got that 28 over 60. And that's in degrees. And so now when I do this, I'm given decimal degrees. So 18 plus 28 divided by 60 is 18.667. That 6 would be repeating. So I'm going to go ahead and round it to 7 there. And then I'm going to use this number in my calculations. And say when I'm done with that, I end up with an angle that's, let me quick get this, 129.5333. So we'll call this angle B, and I end up with an angle A that is 129.5333. Well, what I'm going to do is I need this in minutes. I know that this is the degree portion. So I've got 129 degrees. So what I'm going to do is I'm just going to look at the fraction portion. So I'll subtract 129 from the 129.533 to give me just the 0.533. And so I've got 0.533 degrees, and I need minutes. And I know that 1 degree is 60 minutes. And now the degrees will cancel, leaving me minutes. So I have 0.533 times 60, and that should give me 32. The unit are minutes here. And so in order to do these calculations, what I would do is rather than get a calculator that allows me to input 18 degrees, 28 minutes, I would convert that 28 minutes over to degrees by dividing by 60. And now I have decimal degrees. And I can type 18.4667 in my calculator, take the sign of that, and so on. If my answer is going to be in decimal degrees, like this, 129.5333 or whatever it comes out to be. And so I'll take the integer portion and make that the degrees, so I'd subtract the 129. I'm going to multiply this decimal portion, 0.5333, by 60, like we did over here, to give me the minutes. And now I can type this into my MATLAB. Some calculators will let you type in degrees and minutes. And if so, you can do that. You can just type that in and use degrees and minutes. If you don't have a calculator that will let you type it in that way, go ahead and convert degree minutes over to decimal degrees. And then when you solve the other angle in decimal degrees, just convert that decimal portion over to minutes by multiplying it by 60. Was
Thank
that
you.
what you were asking about?
Yeah, absolutely. Thank you so much. I appreciate that.
Good. Yeah, it has been a while since we did that. So to have it show up all of a sudden is kind of like, oh, that's not what I wanted. Are there any other questions or any other things you want to see worked out? We're actually a minute past time, so I'm glad this is still going. I was afraid it was going to cut us off. All right, if you do have questions, feel free to email me. Feel free to use the discussion board with each other in Blackboard, and we'll see if we can't get through this pretty well. those were the only sections we cover for this week, is law of sines and law of cosines. So take a look at the homework, and I do have office hours Monday through Thursday at 9 in the morning, as well as about 11:15 in the morning. So you can stop by and chat there. I'll also be in office hours this afternoon at about 3. So if you want to stop in, then we can chat as well.
Is there a link in that email that you sent us for your office hours, or is it this link here?
It is the link in the email.
Okay.
Yep, that's also in an announcement on Blackboard, if you can't see your email. All right, well, let's call it, and I'll see, well, have a good weekend. If I see you in office hours, that'll be great. If not, enjoy the homework, enjoy the nice weather. It's supposed to get a little worse this weekend. So for these 2 days, we're gonna have highs in the 70s. It should be great. Hopefully you can hang out in your lawn or something nice. But take care of your loved ones. Have a great day.
Thank you.
You're welcome.